Okay, we're talking about series. Here's two that we looked at last time. So here's a sequence, the sequence C. And what is this sequence approach? What is the limit of this sequence? 3. So what about the series associated with that sequence? Does it diverge? Does it converge? Or is the jury still out? Why does it diverge? Right. So let's show that. Thank you, sir. I had it in my hand walking out the door. Didn't put it in my bag. All right. Jeez. So this graph is going to show value of j, and then it's going to show the partial sums, okay? So the y values of these points I'm going to show you are the jth partial sum for the jth term. So what's the first partial sum? It's just the first term, right? The first term of the sequence. What's the second partial sum? First and 2 added together. So the y value of that point is the second partial sum. Okay, third partial sum. First 3 added together. And so in the long run, what are these terms becoming like? These terms. You told me the limit of this sequence was 3. So in the long run, the terms are all becoming like 3. They're getting really, really, really close to 3. So when j gets really big, we essentially just have a list of 3s. 3, 3, 3, 3. So close to 3 that it's practically the same. So then what happens with the partial sums? So every time we go to the next partial sum, we're effectively doing what? Adding one more 3, or something very close to 3. So what happens? So we look at this as the sequence of partial sums in graph form, right? These y values make the sequence of partial sums. So what's going to happen? So how can we use those partial sums to tell us about the series then? What is the sum of the series? What did we say last time? How can we find the sum of a series if it's not geometric? So with geometric series, we have a formula for the sum, right? A over 1 minus r. But for any other series, how could we find the sum? Or how could we kind of get something that's like the sum? Super important principle here. We don't have a geometric series. We want to get some idea of what the final sum will be of this infinite series. How could we do that? I'm showing you. What are each one of those y values? They're partial sums. What happens when you take bigger and bigger partial sums? It gets more and more like the whole sum, right? The more terms you take on a partial sum, the higher order partial sum you take, the more it's like the whole sum, right? So what's the whole sum going to be? Yeah, it's just gonna get bigger and bigger and bigger without bound, because we keep adding 3. In the end, we just keep adding 3 plus 3 plus 3 plus 3 plus 3. Does it make sense? So this is showing that every change in, every time we take the next partial sum, we're 3 bigger than the one before, or about, getting closer and closer to adding 3 each time. So when j gets really big, and you keep adding these together, it's just going to never stop getting big. So that series diverges or converges? Diverges, right? Now what about this one? This sequence does what? Converges to 0. All right, now what about the series? Can we just definitively say it converges? Maybe, right? So maybe. So let's see. So I've got the partial sums for that one too. So let's start again here. I'll turn on the partial sums for that one. So here's this sequence and its sequence of partial sums graphed. Okay, these are red. What's happening? Every time I take one more higher order partial sum, meaning add one more term from the series, what happens to those partial sums? They're flattening out, right? So the trend is flattening out, meaning what are we essentially adding each time? You have something really small and getting smaller and getting as small as you want. So essentially in the end, we're just like adding 0 plus 0 plus 0 plus 0. That's not till way out in the millions and billions. So that the whole sum might actually be a finite number. If we were able to add all infinitely many terms up, we'd get a finite number because the sequence, the values are getting so small, like 0. So how could we figure out what is this converging to? This series. So we know the sequence converges to 0, but what about the series? How could we kind of get an idea of what the series converges to? Yeah. Okay, what were you going to say? Okay, limit of the partial sums, or if we can't figure out what that limit is, what could we do? Just look at the partial sums and take one that satisfies our precision level. Whatever we want for precision. So here is the table of partial sums for this sequence. Let's zoom in on that. Okay, so these are the partial sums. 1.33, then add the first two terms. 2, add the first 3 terms, add the first 4 terms. And so here's the sum of the first 11 terms is 3.09. Sum of the first 15 terms, 3.18. Sum of the first 100 terms, 3.4. And then 150, 3.41. So now to what degree of certainty do we have here when we get to the 100? The 100 and, smaller, for clarity's sake, is that a little clearer? So when we get to 100 or 150 partial sum, it looks like we're correct to the 10th place, right? We got 3.4 for sure. What if we want more precision? Go farther. So now, at the 300th partial sum, we're up to 3.43. The 400th, still 3.43. Oh, so by the 3,000ths, we got to 3.44. So this is the 3,000th partial sum, 3.44. And so as the terms are getting smaller and smaller and smaller, we're adding smaller and smaller amounts to this. So the partial sum is all it's doing. It's just fine-tuning more and more decimal places of the whole sum. But at this point, we're probably sure it's around 3.44. Will it reach 3.45? Who knows? But probably it's not going to reach 3.6. Okay? So so this is the relationship between partial sums and the whole sum. Any given partial sum is some approximation of the whole sum. And then which partial sums are a better approximation? Higher order, right? Ones that have sum up more terms, right? Sum up more terms. The more terms you include in your partial sum, the better and better approximation it becomes for the whole sum. So let's just put in, so if I put in here y equals, what do you think it is? 3.44. I'm going to put in a line there. Make it a red line because we got the red dots. So the whole sum of this series is something like 3.44, and you see the partial sums getting closer and closer to that value. Okay, and so then we talked about the harmonic series. The harmonic series. 1 over j last time. Does that sequence go to 0? Does that sequence approach 0? Absolutely, okay? These numbers get very small. But then what did we say about the series? So does it converge or diverge? We proved last time this diverges, so let's see the graph. So what's the graph going to look like then? So here's the graph of the first two. This is this sequence converges to 3, and so the series diverges because you can just keep adding 3 forever. This sequence converges to something like 3.44 because you keep, and then at the end you're adding like really small values like 0. So what do you expect to see when I do the same thing for this series from the harmonic sequence 1 over j? What's that going to look like? It's going to level off, straight up. So let's take a look. I'll turn it on first. Can't graph. You could graph it earlier. What are you talking about? Maybe it's because it can't graph it because view doesn't have a value. Okay, there we go. So let's take a look. I hope this works. There we go. So now harmonic is black. What's going to happen? It's going to level off of that red line. It's harmonic series. Oh, it just broke through the red line. It's going to level off eventually. No, so let's let n be a really big value. And let's zoom out, see what happens. So the black one is the harmonic series. Is it going to level off? It will not. It will get to these dots will get to any y value that you want. You just have to get a big enough value of j. It doesn't look like it, but this will not level off, okay? That will keep growing, all right? And we proved that last time, that the sum of the harmonic series is infinite, okay? So it looks like it's leveling off, but it won't. Pick any number, pick 30, 40, 50. Take enough partial sums, that black curve will eventually get up to 30 to 40 to 50 to 100, okay? It will just do it very, very slowly. It will take huge values of j to say, even reach 30, right? To even reach y partial sum to reach 30 will take a really, really big value of j. Okay, so lots of going on in this conversation. First thing is, in order for a series to converge, what has to be true? For a series to converge, what has to be true?
The sequence has to converge to 0.
The sequence has to go to 0. And then if it goes to 0, will this series necessarily converge? No. Some do, some don't. Some do, some don't. So that's where, if your sequence doesn't converge to 0, that's the game over situation. Don't even have to look at that series. It's going to diverge. If it does, the sequence does converge to 0, then we have a question to answer. Will this series converge or not? Will it be like the red one that leveled off at 3.44? Or will it be like the harmonic series that will just keep growing and growing? All right, another important thing here is, if I want to get an idea of the sum of the series, what can I do? What can I do if I don't have a geometric series, I want to get some idea of what the sum is. What's the key to that? What is the key to knowing what the sum of the series is, or getting some idea of what it is? Partial sums. Partial sums they're approximations, right? And the higher order partial sum, the more terms you add in your partial sum, the better approximation it is to the sum of all infinitely many terms. Other questions? Okay, quick review. Take a minute. See if you can complete these sentences correctly. So these are the major. In order for a series to converge, what has to be true? Yeah, Nick.
The sequence must converge to 0.
Yes, he said it word for word. Its sequence must converge to 0. That's really the divergence theorem. If the sequence doesn't go to 0, conclusion, series doesn't converge. It cannot converge unless the sequence goes to 0. The series cannot converge. Okay? What about if the sequence converges to 0? It definitely converges? Maybe. It has a chance. It may converge or it may diverge, depending on the sequence. Right? We've seen examples of both, where the sequence went to 0 Series could, depending on the sequence, the series might converge, might not. What's the value of an infinite series? How do we get the value of an infinite series? We look at what? I want to know what the sum is now. How do we find out what the sum is? What about the partial sums? The limit of the partial sums. When you take the sequence of partial sums, you take the limit. So it's the limit of the sequence of partial sums. And in the one case for geometric series, we know it's a over 1 minus r. But in general, the value of an infinite series is the limit of the sequence of partial sums. Okay? The value of an infinite series can be approximated by what? Do you need a lot? You need a lot of them?
You only need a few,
But I just want to approximate the series. How many do I need? Just one, right? So any partial sum is an approximation. Any partial sum is an approximation. It's just that the first partial sums are not good approximations, and then the ones that have lots of terms are much better approximations. So the more terms in the sum, the better the approximation. Okay, so let's talk about p-series here. And then we'll return to geometric series. Oh, come back. Don't do that to me. There we go. Okay, so with p-series, 1 over j to the p. So the p sequence converges as long as p is positive, right? The sequence converges as long as p is positive. Will the series converge as long as p is positive? Give me an example. What?
it won't converge if p is positive because the harmonic series is just
Yeah. So, right, p equals 1. The sequence will converge. That's the harmonic series, but the series will not. We just proved that. We proved it yesterday. We showed it on the screen today. Okay? So the real question is then, so for what values of p does the p-series converge, and for which does it diverge? All right, let's try p equals 1/2. Does that sequence converge to 0? Does that sequence converge to 0? Sequence. Yes, right? All p has to be is positive, right? So this is 1 over 1, the square roots, right? 1 over square root of 2, 1 over square root of 3, 1 over square root of 4. Does the sequence converge to 0? The sequence? Yes. Does the series converge when p equals 1/2? You could know that right now. You could know that right now. Does anyone know that right now? Does the sequence, the series, the p-series with p equals 1/2, does it converge or not? Some people are saying no. Why not? Okay. The harmonic series has greater values in the denominator. So what does it mean about the values of these fractions? 1 over square root of 2 is, how does that compare to 1/2?
It's greater than.
Greater than 1/2, right? Because it has a smaller denominator. 1 over square root of 3 is greater than 1/3. See where this is going? Will the sequence series converge for p equals 1/2? No. Why? Because we have a series, a sum of things that are, every one of the terms is bigger than the terms of a series we know already diverges. This is called the direct comparison test. We're analyzing this series, the p series for p equals 1/2. We've got this other series we already know the answer to. The harmonic series, every term, so we know the harmonic series diverges, and the one that we're analyzing, every one of its terms are greater than the terms of the one we know diverges. It has to be a bigger sum, right? Bigger than this. And since this gets infinitely big, certainly that will also get infinitely big. It will do it even faster, right? It will get bigger faster. If that was uncomfortable, good. So there should not have been p to the 1/2. Or exponent is p, right? The direct comparison test says that 1 over j to the 1/2 diverges since all of its terms are greater than the terms of the series 1 over j, which we know diverges. So if it's bigger than something that diverges, it also diverges. That's the direct comparison test. Would we have a direct comparison test for series that converge? So what would it be like to have a direct comparison test for a series to prove that a series converges by direct comparison? Tell the person next to you, try to explain that to the person next to you. What would it mean to use direct comparison to show that a series converges? Go.
If we use the harmonics,
Okay, so if you want to show a series converges by direct comparison, you should have said, we need to have another series that converges, that we know converges, and all of its terms have to be
Greater.
okay, so all of the terms in our series has to be smaller than the terms of the series we know converges. Is that what you said? Right, so we've got the one we're analyzing and the one we know converges. All of the terms in ours, every single term would have to be less than or equal to the corresponding terms in the one we know converges, and then we could say ours converges. And this is all in the realm of positive numbers, okay? So I'm talking all in positive numbers there. So, because less than negative, that argument falls apart. So if my terms are all positive, and the series I know converges, and all the terms of mine are less than or equal to the terms of the one we know converges, then by direct comparison we can say the one we're analyzing converges also. Okay? So what if I had a series and all its terms were less than the terms of the harmonic series? What could I conclude? I have a series and all the terms of the series are less than the terms of the harmonic series. What could I conclude? Converges? Diverges? You should be thinking no conclusion, right? There might be some series with all terms less than these that might diverge, but then if you make them small enough, less than this, that's going to converge, right? So direct comparison only works if your series is greater than a series that diverges or less than a series that converges. That's the only way it works. Okay, so that was important, but and you're going to need that for homework and such. Oh, speaking of homework, before I forget, on the homework, 2 things I want to point out. Some of the questions have 1 attempt. Please know which ones those are. Think through them very carefully, and maybe confirm it with another student in the class what they're thinking. So, because we want you to get the points, we do want you to get the points, but there's 2 choices, so we can't give you 2 attempts. So, just make sure you know which questions those are, and tread lightly, tread carefully. Okay. The other thing is the second half. There's going to be questions about alternating series, which we'll get to on Monday. So this is due Wednesday morning. So, and then I'm going to post another. We'll see. But anyway, so you can push forward and just know that there's coverage in class Monday that pertains to that homework. So if you feel like we haven't covered that yet, you're right, okay? That's alternating series. Okay, so going back to this question here, for what values of p does the p series converge? Certainly, it diverges if what? Yeah, so the p series certainly diverges if it's just less than 1? We know that for sure. So the question is, does the p series converge if p is greater than 1? Did we see an example of that? I should say A. So we saw the one I showed you, the 4 over I squared plus 1 or something like that, or plus 2, something like that. That's essentially, what was that? Was it 4 over p squared plus 2? I squared plus 2? Is that the one we did in class? The one I showed you the graph of? Okay, that's very close. That's like a p series with p equal to 2. But it's not because of this plus 2 in the denominator. So the plus 2 is kind of trivial for the question of convergence or divergence, but because there's a plus 2, it's not officially a p series. But it's really close. It's really similar. For all practical purposes, in terms of convergence and divergence, we can just consider this a p series with p equal to 2. And what about that one? Converge or not? It did, right? This we saw this converged to, what, 3.44 or something like that. Okay, so what is the breaking point? So 1, it diverges to p equals 2, converges. So without proving it, I'm just going to tell you, just for time's sake, as long as p is greater than 1, the p series converges. So there's just too many things to do. I don't have time to prove that to you. I would love to. But we had a good discussion about it with the p equals 1/2. We saw one that does converge there with p equals 2. So 1 is the breaking point. If p equals 1 or p is less than 1, it diverges. If p is greater than 1, it converges. So why is a higher value of p helping this thing to converge, right? So why is a higher value of p helping the series to converge? Because what does a higher value of p do? Yeah, so it makes the denominator big faster, right? The higher p is, the faster this thing gets small. Come back. It's showing me the light, but it's not doing it. Oh, you can do it. All right, I'll just use this. Okay, so the bigger that p is, the smaller those get faster, and that's the determining factor. Do they get small enough fast enough for it to sum out to a finite number? Or do they not get small enough fast enough, like the harmonic series, and just keep growing? Okay, back to geometric series. Let's talk about geometric series again. Lots to do today. So we did the proof of when does this geometric series converge? What did we say? For the same values of r that the sequence converged, right? So that's different than the p series, right? With the p series, the sequence converges if p is positive, greater than 0, but the series converges only if p is greater than 1. For a geometric series, it's the same as the sequence. If the sequence converges to 0, then the series converges. So that determining factor is r between -1 and 1. And then in proving that, we also found out what the geometric series converges to. What does the geometric series converge to? Yeah, so here's the one example where we actually get a precise, exact value for the sum. When a geometric series converges, its sum is a over 1 minus r. This may have officially died.